In this screencast, we're going to solve systems of equations that involve three variables, three equations, using some of the techniques that we used for two variables and two equations. So if we think about a line being a 2D shape created by a two-variable linear equation, if we take three variables in three dimensions and put it in a linear equation, that actually becomes what we call a plane. The plane connects an infinite number of points that satisfy the three-variable linear equation, and it also goes in three dimensions. What you see here is an example of a plane with the equation 6x plus y plus 3z equals 18. So you notice the shape is in three dimensions, and it represents the set of all points that satisfy this linear equation. Instead of being a line, it's actually a plane, which is like a piece of paper that goes on forever in all directions. So if we look at the possibilities that occur when we take three of these planes and we put them together, just like three linear equations, we see a number of different possibilities occur. So the one in the upper left-hand corner here is when the three planes come together at a point. That point with coordinates x, y, z is the solution to that linear system of three equations. The next case occurs when the three planes come together as a line. This is a consistent and dependent situation. It's also possible for all three planes to be the same. This is very similar to them being the same line with two equations. This is consistent and dependent as well. The four situations on the right are all examples of there being no solution, an inconsistent system. So now let's go ahead and solve a three-variable system of equations with three equations and three variables. The basic technique is going to be to try to get it down to two variables with two of the equations by eliminating one of the variables, repeating that procedure, then solving for, thereby determining one of the variable values, and then plugging that value back into the preceding equations to come up with the ordered triple, that is the x, y, z solution if it exists. So let's jump right in. We're going to use elimination to make a system of two equations and two variables. And so we're going to take these first two equations and work with them. And a lot of different things we could do here, but what we're going to do in this particular case is multiply the bottom equation here, which is the second of the three, by -2. By doing so, we're going to add the two equations and eliminate the z variable. Okay, so we take the first equation and then we multiply the second equation by 2. We have 4x plus 2y minus 2z equals 10 as the second equation. And notice now when we add them together, the z's are going to cancel each other out. Don't forget, you multiply all parts of it by 2, including the right-hand side. When we add these two equations together, we get 9x plus 5y equals 12, and that becomes an equation with two variables and two unknowns. Notice that z is gone. That's a good thing. So now we're going to take the first equation and the third equation. Now, you could have also taken the second equation and the third equation. And we're going to multiply the third equation by -1. In doing so, that will also eliminate the z. So when we take -1 and distribute it to all three of those terms on the left, and -1 to the term on the right, and we add them together, we get 5x minus 1x, which is 4x. And then we get 3y minus 4y, which is -1y. And the z's again cancel out. So notice we now have a second equation with two unknowns, x and y. So now we can take the result of these two operations, which have both eliminated z, and we can now find x and y. Yes, this is a very involved process. So now we're going to solve the system of two equations, 9x plus 5y equals 12, and 4x minus y equals -14. Again, lots of ways we can do this. Probably the easiest here is to go ahead and multiply this second equation by 5. When we do so, that equation becomes 20x minus 5y equals -70 when I multiply all three of those parts by 5. Why do I do that? Because the y's are eliminated when you add. 5y minus 5y is equal to 0y. 9x plus 20x is 29x. And we add the right-hand sides, 12 minus 12 plus negative 70, we get negative 58. Then we're going to divide by 29 using the division property of equality. And we get our first part of the ordered triplet, which is that x value is negative 2. So we know now that the solution has the coordinate x equals negative 2. Well, now we're going to take the negative 2 and substitute it in to find y. We'll take either one of the equations that only involve x and y. How about 4x minus y equals negative 14? Now we're going to substitute in a negative 2 for x. And so we get negative 8 minus y equals negative 14. Then we're going to use the addition property of equality to move that 8 over. And we're going to divide by negative 1 after we do that. And we get, using the division property of equality, we get y equals 6. So now we've got two pieces of information. X is equal to negative 2, y is equal to 6. We only need one more data point to get that ordered triple that includes the three coordinate solution. So negative 2 and 6 for x and y respectively. Now we solve for z using one of the original equations with three variables, because now we know x and we know y. So pick the easiest one to work with. 2x plus y minus z equals 5. Okay, so we'll substitute a negative 2 for x and a 6 for y. And we're left with one equation, one unknown, negative 4, because negative 2 times 2 is negative 4, plus 6 minus z. So we're going to combine those like terms and get positive 2. We're going to move that 2 over using the subtraction property of equality, and we get negative z equals 3. Then we have to divide by negative 1 to get that z equals negative 3. We now have the entire solution. We now have the entire solution to the mystery, which is that the solution, the ordered triple, negative 2, which is the x-coordinate, 6, which is the y-coordinate, and negative 3, which is the z-coordinate, in three-dimensional space, is the solution to that set of three equations, three unknowns. The three planes happen to meet in a point. You should always go back and check this with the original other equations to make sure that it worked. So we've looked at what systems of three equations and three unknowns look like, and we've developed a process using elimination and substitution methodically to solve for it.